Imagine our solar system, this place we think we know so well. We've charted the planets, sent probes flying past.
We've got maps, right? Detailed maps.
Exactly. Decades of exploration, and yet, for years now, scientists have been chasing this idea, something huge, maybe the biggest secret our solar system still holds, a kind of cosmic ghost.
It really is like that. A ghost in the machine, almost. Because the evidence isn't, a direct sighting. It's indirect. It's how this thing seems to be affecting other objects way out there.
A gravitational whisper, they call it sometimes.
That's a good way to put it.
Yeah.
It's like feeling a draft and knowing a door must be open somewhere, even if you can't see the door itself.
And that's what we're diving into today, this incredible hunt for that mysterious ninth planet, Planet 9. But here's the really cool twist we want to explore.
Yeah, the approach has kind of shifted, hasn't it?
It really has. Instead of just trying to catch that incredibly faint sunlight bouncing off it, which, imagine how hard that is at those distances.
Almost impossible, practically.
Right. So the new idea, this ingenious approach, is to look for its heat, its own internal warmth, like a faint glow.
It's a totally different way of thinking about detection, looking for the object's emission, not reflected light from the sun.
So in this deep dive, we'll unpack that whole puzzle. How did the idea even start? What are those gravitational clues?
The Kuiper Belt connection.
Exactly. And then we'll get into the nitty-gritty of these new techniques, this thermal approach. And finally, the really exciting part, the new candidates that just might be our first real glimpse of this hidden giant.
It's a fantastic story of, scientific creativity, really, pushing the boundaries of how we even look for things in space.
And we're basing this on some really fascinating stuff. Recent articles from Universe Today, pieces like Hunting Planet 9's heat signature and the elusive Planet 9, a new candidate emerges.
And that core research paper, the one published in the publications of the Astronomical Society of Australia, a far infrared search for Planet 9 using AKARI all-sky survey. That's really central to this new thermal hunt.
Yeah, these give us a really detailed look at the cutting-edge methods being used. It's one of the biggest mysteries right in our cosmic backyard. So let's get into it.
Let's do it.
Okay, first things first. What exactly is Planet 9? Because we need to be clear, we're not talking about Pluto getting its old job back, right?
No, definitely not. Pluto's reclassification is a whole other story. This is something entirely different, a hypothetical, massive, undiscovered planet. Way bigger than Earth, potentially. Something distinct from the 8 we know.
A potential new major player in the solar system.
Exactly. And the idea didn't just pop out of nowhere. When Badgett and Brown first proposed it back in 2016, they weren't just guessing. It was based on these really weird patterns they saw in the orbits of objects way out beyond Neptune. Things just weren't moving randomly out there.
Right, it was inferred, like you said, like cosmic forensics, looking at the effect to figure out the cause.
Precisely. And over time, the research has painted a pretty specific picture of what this thing might be like. Its size, for instance.
Yeah, I saw some figures like 5 to 10 times the mass of Earth.
That's one estimate, yeah. The research paper we're looking at, drawing on simulations by Milholland and Laughlin, ML17 they call it, puts it more like 6 to 12 Earth masses.
Okay, so definitely hefty. A super Earth or maybe a mini Neptune type thing.
Potentially. Brown and Baddigan's later work in 2019 even refined it to around 6.2 Earth masses, give or take. So we're talking substantial.
And these numbers aren't just abstract, right? They actually guide the search.
Absolutely critical.
Right.
Knowing the potential mass helps predict its gravity, which links back to those orbital clues. But maybe even more important is the distance.
Which is just mind-bogglingly far.
Isn't it? Estimates range from, say, 400 to 800 times farther from the sun than Earth is.
400 to 800 AU.
Yeah, or even 400 to 900 AU in some simulations, with an average orbit maybe around 650 AU. Just think, Neptune's at 30 AU. This thing is way, way out there.
In the deep freeze, basically.
Totally. Which brings us to its temperature. Estimated to be incredibly cold, maybe 28 to 53 Kelvin. That's just barely above absolute zero.
So not much heat, but crucially, it's internal heat, right? Not reflected sunlight.
That's the key point for this thermal search. It's radiating its own faint warmth, left over from formation, probably, not relying on the sun, which is just a distant star from out there.
And its orbit isn't neat and tidy like the inner planets either.
No. Predictions suggest it's likely on a really stretched out elliptical path, highly eccentric, maybe around 0.45 eccentricity.
And tilted, too, not flat with the others.
Right, significantly inclined, maybe 16 degrees, maybe even 30 degrees relative to the main plane of the solar system. And again, knowing this predicted orbit, the eccentricity, the inclination, the likely distance, tells astronomers where in that vast sky they should be focusing their efforts.
So, okay, a big, cold, distant world on a weird orbit, glowing faintly with its own heat. But what first made scientists think, hang on, maybe there's something else out there? What was that gravitational whisper?
It all comes back to the Kuiper Belt. Specifically, these small icy bodies, called Kuiper Belt Objects, or KBOs, that orbit way beyond Neptune.
The ones with the strange orbits.
Exactly. Astronomers started noticing that a certain group of these KBOs, the ones with the most distant, elongated orbits, they call them extreme TNOs, trans-Neptunian objects, weren't scattered randomly.
They were clustered.
Yeah, their orbits seemed to be sort of pointing in the same general direction in space. Specifically, the perihelion direction, the point in their orbit closest to the Sun, was oddly aligned for several of them. And their orbital planes were tilted similarly, too.
That doesn't sound random at all.
It really doesn't. The odds of that happening just by chance were calculated to be incredibly low. Badigian and Brown, in their original paper, put it something like 0.007%. Tiny.
Wow.
So the leading explanation became this idea of gravitational shepherding, that there must be a big unseen planet, Planet 9, whose gravity is gently nudging these KBOs over millions and billions of years, corralling them into these aligned orbits.
Like an unseen cosmic sheepdog herding the KBO flock.
That's a perfect analogy. Its gravity sculpts their paths.
But science being science, this wasn't just accepted immediately, right? There was pushback. Debate.
Oh, absolutely. And that's healthy. A major counterargument was observational bias.
Meaning, we only see the ones that are clustered because our telescopes happen to be looking in the right place at the right time.
Kind of, yeah. Or maybe the way we conduct surveys makes it easier to find objects with certain orbital properties, creating an illusion of clustering. Some big surveys, like the Outer Solar System Origin Survey, OSOS, and the Dark Energy Survey, DES, initially reported finding extreme TNOs that seemed more uniformly distributed, casting some doubt.
So a real puzzle. Is the pattern real, or is it just how we're looking?
Exactly. It forced everyone to really scrutinize the data, the survey techniques, the potential biases. How do you know you're seeing a true pattern and not just an artifact of your limited view?
That must be incredibly difficult when you're talking about finding tiny, faint objects scattered across such a vast area.
It is. But, and this is crucial, the proponents of Planet 9 didn't just ignore this. They went back, refined their simulations, and specifically work to account for these known observational biases.
And what did they find then?
Well, a very recent paper, just this year actually, by Badigian and colleagues, presented new simulations. They incorporated these biases, basically asking, even accounting for how we look, is this clustering still statistically significant?
And the answer?
The answer was yes. Looking at the perihelion distribution of 17 of these long-period TNOs, they found that the results still rejected the absence of Planet 9, the no Planet 9 scenario, at a confidence level of about 5 sigma.
5 sigma, that's the gold standard, right? Like discovery level significance in physics.
It is. It means the probability of this clustering being a random fluke, even after accounting for observational biases, is incredibly tiny, less than 1 in 3.5 million. So the statistical evidence for something massive lurking out there and causing this pattern is now very, very strong.
Okay, wow. So the gravitational hints are pretty compelling now. But that just makes the next question even more pressing. If the evidence is so strong, why haven't we just seen it yet? Why is it still a ghost?
Well, that comes down to the sheer, brutal difficulty of actually detecting it directly, especially using traditional methods, meaning looking for reflected sunlight.
Because it's so far away, the sunlight reaching it is already weak, and then only a tiny fraction reflects back towards us.
Exactly. And light intensity drops off incredibly fast with distance. If you double the distance to an object, the reflected light you receive from it becomes 16 times fainter.
16 times?
Yep, it follows an inverse fourth power relationship. Distance squared going out, distance squared coming back. It's a killer for detecting faint objects at extreme distances.
So even our best optical telescopes are just struggling to pick up such a faint pinpoint of light hundreds of AU away.
They really are. There have been massive efforts using powerful wide-field surveys, things like the Zwicky Transient Facilities ETF, the Dark Energy Survey, TES, pan-stars. They've scanned huge swaths of the sky.
And found nothing matching Planet 9.
They've managed to rule out a Planet 9 brighter than a certain limit, say magnitude 21 out to maybe 500 AU or so. But beyond that, or if Planet 9 is fainter, it could easily still be hiding in the data, just too dim to reliably pick out.
They tried infrared too, right? With WISE and NEO-WISE.
Yes, searches in the near-infrared were also conducted, again without success in finding Planet 9 itself. It really highlights the limitations of relying on reflected light for something this distant and likely cold.
Okay, so reflected light is a dead end, or at least an incredibly difficult path. This is where the paradigm shift comes in. Tell us about hunting for the warm glow instead.
This is the really clever part. The core idea, championed by researchers like Amos Chen's team, whose work we're focusing on, is to stop worrying about reflected sunlight and instead look for the planet's own heat, its thermal radiation.
Because everything warmer than absolute zero gives off some heat, some infrared light.
Precisely. Even something incredibly cold like Planet 9 at maybe 30 or 40 Kelvin will still radiate faintly in the far infrared part of the spectrum.
And the big advantage here is how that thermal signal fades with distance, right? It's different from reflected light.
Massively different. This is the key physical advantage. Thermal radiation follows an inverse square law, not inverse fourth power. So if you double the distance, the heat signal only becomes 4 times fainter, not 16 times.
Okay, 4 times fainter is still a big drop, but it's way, way better than 16 times fainter when you're talking about these enormous distances.
It makes a huge difference. It makes detecting a faint, distant object significantly more feasible if you have the right instrument looking in the right part of the spectrum.
And that right part is the far infrared.
Yes. Based on Planet 9's estimated temperature range of 28 to 53 Kelvin, its thermal emission should peak somewhere between about 50 and 100 micrometers. That's firmly in the far infrared.
So you need a telescope specifically designed to see those wavelengths, and crucially, one that's not blinded by Earth's own heat.
Exactly. Which brings us to the AKARI space telescope.
The Japanese mission.
That's right. Launched in 2006, AKARI was an infrared astronomy satellite. It had a cooled telescope about 68 centimeters, specifically designed for sensitivity in the infrared. And critically, it performed an all-sky survey in the far infrared, the most sensitive one ever done at those wavelengths.
Being in space was key then, to get away from the atmosphere.
Absolutely vital. Our atmosphere glows brightly in the infrared, and it absorbs a lot of the incoming infrared light from space. Ground-based far-infrared astronomy is incredibly difficult. AKARI, being up in orbit, had a clear, cold view of the universe.
And it had the right instruments.
It did. Its far-infrared surveyor, or FIS instrument, had filters covering that crucial 50 to 180 micrometer range, perfect for potentially picking up Planet 9's heat signature.
But I remember you mentioning that the standard AKARI catalogs weren't ideal for this search. They had to use something different.
That's a really important detail. The standard official AKARI catalogs, like the FIS Bright Source Catalog, FIS-BSC, were built to find stationary sources, stars, galaxies. They did this by requiring that a source be detected multiple times in the exact same spot over different scans.
Which would automatically throw out anything that moves like a planet.
Precisely. Planet 9, even though it's distant, would still show apparent motion over time due to parallax in its own orbit. So it wouldn't meet the criteria for the standard catalog.
So what did they use instead?
They used a more specialized, less restrictive list derived from the AKARI data called the FIS Single Scan Detection List, or FISSDL. This list basically includes any potential source detected at least once in a single scan.
Ah, so it keeps the moving objects in, but I guess it also keeps a lot more noise and false signals.
That's the trade-off. You increase your chances of finding something real and moving, but you also drastically increase the number of potential contaminants. Cosmic ray hits, instrument glitches, faint background galaxies. It makes the filtering process afterwards absolutely crucial.
Before Chen's team did their work with this specific list, were there earlier attempts to use thermal data?
Yes, definitely. People recognized the potential of thermal detection early on. There was theoretical work suggesting microwave detectors might work.
Right.
And in the far infrared, Rowan Robinson used data from AKARI's predecessor from the 80s and found one potential candidate, but it didn't quite fit the expected profile.
Okay.
Then Sedgwick and Sargent used both IRAs and the standard AKARI catalog. They initially flagged over 500 candidates.
Wow. That sounds promising.
It did, but most of them turned out to be contamination from galactic cirrus.
Ah, space dust. Those faint, wispy clouds in our own galaxy that glow in the infrared.
Exactly. They can easily look like faint point sources if you're not careful. So while these earlier searches were pioneering, they faced significant challenges with sensitivity and contamination. Chen's team, by using AKARI's deeper data and the more inclusive FIS-SDL list, could push significantly fainter, about 5 times fainter than IRAs could reach.
Okay, so Chen's team has the right idea, look for heat. They have the right tool, AKARI, and they're using the right, albeit messy, data set, the FIS-SDL. But that list had over 5 million potential detections. How on earth did they sift through that to find Planet 9 candidates?
With extreme care and a multi-layered filtering process, it's really a masterclass in meticulous data analysis. Think of it like a series of increasingly fine sieves.
Okay, sieve number 1.
Position selection. They didn't search the entire sky. Based on the simulations predicting Planet 9's likely orbit, especially its inclination and perihelion direction.
The zones where it was most likely to be.
Right. They focused on a specific patch of sky roughly between 30 and 50 degrees right ascension and negative 20 to plus 20 degrees declination. This immediately cut down the 5.27 million sources to a more manageable, though still huge, 50,000 or so.
Still daunting. What's the next filter?
Excluding known stationary sources. This was crucial. They took those 50,000 sources and cross-matched them against 9 major astronomical catalogs. Optical ones like Pan-STARRS, infrared ones like WISE, and 2MASS.
The idea being, if a source shows up in the same spot in multiple catalogs spanning different times or wavelengths, it's probably just a regular star or galaxy, not Planet 9.
Exactly. If it's stationary, it's out. They used very precise matching radii, like just a few arc seconds, to make sure they weren't accidentally throwing out something real. This step was huge, bringing the count down to about 29,900.
Okay, getting better. What's next? Removing faint or unreliable signals.
Yep, flux selection. First, they required a good quality detection, specifically at 90 micrometers, which is AKARI's most sensitive far infrared band. The signal had to be at least 5 times stronger than the estimated error. Reliable data only.
Makes sense.
Second, they actively filtered out sources likely contaminated by that galactic cirrus, the space dust. They used a measure of the background infrared brightness. If the background was too bright, they assumed the source might just be a knot in the dust, not a real object. This dropped the number to about 1,700 candidates.
Now we're talking. Down from 5 million to 1,700. But the key is motion, right? How did they filter for that specific Planet 9 movement?
This was the most clever part. Detection, selection for motion. They exploited how Planet 9 should behave according to theory. Because it's so distant, it should look almost stationary over a short time, like hours during a single AKARI observation session.
Okay.
But over months, as Earth moves in its orbit, Planet 9 should show a noticeable shift due to parallax, a wobble against the background stars, maybe 10 to 25 arc minutes over 6 months.
A specific signature
Yeah.
still for hours moving over months?
Exactly. So they looked for sources in the FSDL that were not confirmed at the same position 6 months later, ruling out stationary objects. They also required more than one detection in the 90 micrometer band initially. This crucial step narrowed it down to 393 candidates.
393. Close enough to start looking really closely, maybe even by eye.
That's exactly what came next, image inspection and final filtering. This involved visually examining AKARI's detection probability maps for each of these 393 candidates.
Checking if they look like real point sources, not just noise.
Precisely. They set a threshold for how point source-like it had to look. This got them down to 369. Then, they applied that motion criteria visually. Was it detected at least twice within 24 hours, short-term stationary? And crucially, were there no detections at the same spot 6 months later? Long-term movement. This confirmed parallax check reduced the list to 165.
Still a lot of work. What else could trip them up at this stage?
Cosmic rays were a big one. These high-energy particles hitting the detector can create false signals, especially near the South Atlantic anomaly. They had to visually identify and remove candidates that looked like characteristic cosmic ray hits. That took out almost 100 candidates, leaving 67.
Wow. Cosmic rays are a real pain for these sensitive searches.
They really are. Then they removed a few candidates detected right on the edge of AKARI's scan paths, if those are less reliable, down to 13. Then they found 3 objects that were moving too fast, several arc minutes, in just hours.
Probably asteroids closer in.
Most likely, yes. New uncatalogued asteroids, so not Planet 9. That left 10 candidates.
10. Getting really close. What was the absolute final check?
The one-year scan check. AKARI sometimes scanned the same patch of sky roughly a year apart. Over a year, the parallax effect mostly cancels out, and you'd mainly see Planet 9's slow orbital motion. It's proper motion. They check if any of the 10 candidates had another detection about a year later, offset by the expected proper motion. If they did, and if that other detection was stationary or matched something else, it ruled out the candidate.
So after running this incredible gauntlet, filtering millions down through layer after layer of checks, what was left?
Just 2 candidates survived this entire rigorous process.
2 potential Planet 9s. That's amazing. Tell us about them.
Okay, the 2 candidates are designated FISSDL J02504221501111, detected in July 2007, and FISSDL J03011111164240, detected in July 2006. They both showed up in the 90 micrometer band, had fluxes consistent with predictions, and crucially showed that pattern of detection within 24 hours, but no detection 6 months later.
And the team checked if these 2 could be the same object seen in different times.
They did. They looked at the separation between these 2 candidates, and some other uncertain ones they'd set aside. But the angular distances were too large to be explained by Planet 9's predicted parallax over the time between observations.
So potentially 2 different candidates, not just one object caught twice.
Based on their analysis, yes.
Yeah.
They appear to be 2 distinct candidates at this stage, which is fascinating in itself.
Absolutely mind-blowing. But Chen's team wasn't the only one using this thermal approach, right? You mentioned Terry Longfan's team took a different tack.
That's right. It's a great example of complementary strategies. Fan's team also used far infrared data, but they combined AKARI data with observations from its predecessor, IRAS, taken way back in the 1980s.
So they had a much longer time baseline.
Exactly, a 23-year baseline. Instead of looking for the 6-month parallax wobble like Chen's team, they were looking for Planet 9's slow orbital motion over 2 decades. A much smaller apparent motion per year, maybe 3 arc minutes, but over 23 years, it adds up to a detectable shift.
So Chen looked for the Earth's motion reflecting on Planet 9's position, while Fan looked for Planet 9's own motion around the sun. Clever.
Very clever. They used a specific AKARI dataset designed for finding moving objects by comparing with older surveys. They estimated the expected flux and motion, searched for matches between IRAS and AKARI sources separated by the right amount.
And did they find anything?
They initially found 13 potential pairs. After careful vetting, checking for consistency with a slow-moving object and ruling out other possibilities, they narrowed it down to 1 strong candidate pair.
1 candidate from this decades-long search.
Yes, an IRA source from the 80s and an AKARI source from the 2000s, separated by an angular distance consistent with Planet 9's predicted orbital motion over 23 years, for a certain range of distances and masses, and crucially not seen in the same spot in both surveys.
But again, just like Chen's candidates, this is still just a candidate, right? Not confirmed.
Correct. 2 data points, even 23 years apart, aren't enough to definitively calculate an orbit and confirm it's a planet. It's another incredibly promising lead that absolutely requires follow-up.
It's fascinating comparing these. Chen's team uses only AKARI, focuses on parallax, potentially probes deeper, maybe out to 800 AU. Fan's team uses IRS and AKARI, focuses on orbital motion over decades, perhaps better suited for slightly closer ranges, maybe 500, 700 AU.
It shows there's more than one way to skin this cosmic cat, so to speak. Different methods probing slightly different possibilities, which strengthens the overall search.
So we have these candidates, 2 from Chen, 1 strong, 1 from Fan. The obvious question is, what now? How do we go from candidate to confirmed planet? And what about potential false alarms?
Right. Dealing with potential false alarms is always paramount. Could these detections be something else entirely? Maybe a rare flaring object far out in space, like a distant supernova?
A transient event.
Exactly. But the teams calculated the probabilities. The chances of a supernova or a nova or a star being ripped apart by a black hole, happening in just the right spot, mimicking Planet 9's faintness and specific motion pattern, well, the odds are incredibly low.
Like astronomically low.
Pretty much. Chen's team estimated maybe 0.014 supernovae expected in their whole survey window. The chance of one perfectly faking a Planet 9 detection is negligible. Same for just random noise fluctuations in the detector accidentally lining up the filtering was designed to make that extremely unlikely.
Okay, so contamination seems unlikely, though never impossible. That really puts the focus on the next step.
Which is follow-up observations. That's the critical, unavoidable bottleneck. The AKARI or AKARI detections give us tantalizing hints, 2 points on a potential path. But you need more points to define the orbit.
You need to track it, see if it keeps moving as predicted.
Precisely. You need more powerful telescopes, likely ground-based optical or near-infrared ones, to try and spot these candidates directly, now that we know exactly where to look.
Which telescopes are up to the task?
Telescopes like Subaru in Hawaii, with its hyper-suprime cam. It has a wide field of view and incredible sensitivity, capable of detecting objects down to magnitude 26, which might be faint enough to catch Planet 9, especially if we know where to point.
How long would that take?
The estimates suggest just a few targeted pointings, maybe less than 10 minutes of exposure time per candidate, could be enough to detect something that faint with Subaru. The Dark Energy Camera, DCAM, is another major instrument capable of this kind of follow-up.
And these follow-ups would tell us?
They would tell us if the candidate is still there and if it has moved consistently with the predicted orbit of Planet 9 over the time since the AKARI detections. More data points allow calculation of a precise orbit. This would definitively rule out background objects or confirm we found something truly extraordinary moving within our own solar system.
So if one of these candidates, or perhaps a future one found by these methods, gets confirmed, what does that mean? What are the implications?
Oh, they're immense. Truly revolutionary. First, it would fundamentally change our picture of the solar system. Our neat model of 8 planets would be instantly outdated. We'd have a whole new class of planet, a distant super-Earth or mini-Neptune shaping the outer reaches.
It would rewrite the textbooks on solar system formation and evolution.
Absolutely. How did it get out there? Was it kicked out? Did it form there? It opens up a floodgate of new questions and research avenues. And of course, it would finally explain that weird clustering of the Kuiper Belt objects.
The original gravitational whisper that started it all would finally have its source identified.
Exactly. That long-standing mystery would be solved. And just think about the method itself, finding it by its heat. It's a powerful demonstration of scientific ingenuity. When one path is blocked, find another way. Don't just look harder, look differently.
Feel its warmth instead of searching for its reflection.
A perfect summary. It shows that even in our own cosmic neighborhood, there are still potentially huge discoveries waiting if we're clever enough about how we search.
It really is an amazing cosmic detective story we've gone through today. From those first weird clues out in the Kuiper Belt.
The subtle gravitational hints.
Right, to this complete shift in strategy for getting reflected light, focusing on that faint, far-infrared heat signature.
And the incredible painstaking work using telescopes like AKARI, sifting through millions of data points.
By teams like Chen's and Fan's, applying these super clever filtering techniques to pull out just a handful of truly promising candidates. It feels like we're right on the cusp.
It really does. It's such a testament to, human curiosity, that drive to understand our place in the cosmos. And it shows that even our own solar system, which feels so familiar, might still hold profound surprises.
The journey's definitely not over yet. We need those follow-up observations. But it feels like the dream of finding a true 9th planet is, well, closer than it's ever been.
The next few years of observations could be incredibly exciting.
So, as we wait for those results from telescopes like Subaru, here's something to think about. If we're still finding potential massive worlds right here in our own backyard, just by changing how we look, switching from light to heat, what else might be out there?
Good question.
What other secrets is the universe hiding, just beyond the limits of our current ways of seeing? What other faint glows or maybe entirely different kinds of signals are out there waiting for us to figure out a new way to perceive them?
It definitely makes you wonder what discoveries lie just over the horizon, waiting for the next ingenious idea.
The universe always seems to have more surprises up its sleeve.